Hey guys. So in this unit, we've done a lot of graphing. We've done a lot with the scattering reports and everything like that. Something we haven't done much yet with acceleration is calculations. So today we're going to learn a couple more equations that we can use to find out attributes about things moving that are accelerating. All right, so first, we need to remember the definition of acceleration. The reason I have this kind of open parentheses right here is we need to um, write down what symbol we're going to use for acceleration. And we talked about this before. We just use the letter A. Sorry, it's kind of big there, but the letter A is our symbol that we use for acceleration. The definition for acceleration is that anything that is changing speed is accelerating. So acceleration is a change in velocity. Sorry, my handwriting's bad on this pad. Over time. I'll get better as we go. Okay. Change in velocity over time, that's the definition for acceleration. Therefore, straight from the definition, the equation for acceleration would be acceleration equals change in velocity. So the symbol we have for change is delta. So delta v over time. So an amount of time would be delta t. Acceleration is change in velocity divided by change in time. Okay, this is the equation for acceleration. And since we're in the acceleration unit, this is the main equation. All other equations will come from this equation right here. Okay, so let's look forward. Looking at a velocity graph, last unit, things went at a constant velocity. And what that meant on a velocity graph was one straight line that was flat. All right. Now that things are accelerating on velocity graphs, we don't see flat lines, we see lines that are sloped. They can be sloped downward. If it's going towards zero, it's slowing down. They can be sloped upward, but they have some sort of slope to them, right? So if a line has a slope, if it has that tilt to it, we can find the slope. We pick 2 points on the line, say 1, 2. You can do rise, up, divided by run. Kind of sloppy. Let's think about what that slope actually is. The rise is how much this velocity is changing. So the rise is the delta v. The run is how much the time is changing, delta t. So when you divide rise divided by run to find the slope, the rise is delta v, the run is delta t. Rise divided by run. That's our equation for acceleration. So what this means is that the slope of a v versus t graph is acceleration. And you should have remembered that from your scouting reports, but I wanted to remind that to you because you'll be doing that a lot. All right, so now let's talk about units. So let's go back to this graph. Velocity we usually measure in meters per second. Time, almost always just in seconds. So you saw this a little bit with the scouting report. If you're taking meters per second and you're dividing it by another second, it can be written as meters per second per second. Now that's a lot to say and it's kind of a lot to write as well. So we can combine these 2 seconds. Technically they're both within the denominator, so they combine to be meters per second squared. Okay, and that's how I'm always going to be writing it. On the board, on assignments, on the test, you'll see it as meters per second squared. If it makes more sense to you to write it as meters per second, that's completely fine. You can write either of these, but just know that you'll be seeing it as meters per second squared. All right, great. So we talked about if an object is accelerating, then its velocity is changing. This means if your velocity is changing, that you start with a velocity and you end with a velocity. So this means it has a starting velocity, so I'm just going to put v, starting velocity, and an ending velocity. And we're going to have a symbol for each of those. And you've seen these before. So if you have a starting velocity, we're going to call that v with a little I below it, a little subscript I. And you've seen these before with position in the first unit. This means initial. So this would be initial velocity. V with a little f, final velocity. Okay, I give you these symbols because we're about to put them into an equation. So we can change our original equation to form new ones. Like I said, all of our equations come from that first one. Acceleration is change in velocity divided by change in time. All right, we learned in the first unit that if you have a change in something, like a change in position, to find the amount of change, you take the final minus the initial. So that's exactly what we're going to do. In this equation, for delta v, I'm going to plug in v final minus v initial. So acceleration equals v final minus v initial. And then still divided by that delta t. All right, so now we're starting to get some more attributes into this original equation. I'm not going to go through all of the math, but most of you will be able to see in your head, if you solve this equation for Vf, it's fairly simple. It's going to give us our motion equation number 1. So what you'd end up doing is multiplying delta t to both sides, and then adding Vi to both sides. If you do that correctly, what you'll end up with is velocity final is equal to velocity initial plus acceleration multiplied by time. This is known as motion equation number 1. So this is going to be on the board along with our original acceleration equation during your test. All right, flip the page over, and it tells you if there is a motion equation number 1, then surely there's a motion equation number 2. This one we could also go through and figure out how to do it mathematically, but it's a little bit more complicated, so I'm just going to give it to you. Motion equation number 2. This is an equation for delta x, or distance. So if something is accelerating, you know how far it will move. Now this one's a little bit more complicated. The distance equation is velocity initial multiplied by time plus 1/2 acceleration multiplied by time squared. That's motion equation number 2. It's longer, but we'll have some practice using it. A lot of people ask, this squared, it's not for the entire 1/2 at, it's just for the time. Only the time is the squared variable here. All right, so we will use all 3 of these equations to find attributes of accelerating objects. Sorry if you run out of room, I'm going to also. Accelerating objects. So depending on what equations we use, we can find out different things. All right, let's see if we can actually do some. So example 1, very standard. A firework accelerates from a speed of 0 to a speed of 30 in 3.5 seconds. What is the acceleration of the firework? All right, so what I think is going to help some of you, if you don't know how to start on problems like these, I suggest that you go back to what we called the guess method. Now this is a very straightforward problem. If you think you can do this problem or any of the other 6 problems on your own, go for it. I'm not telling you You have to follow along with the video. I'm not telling you you have to use the guess method, but for those of you that might need the extra support, that's how I'm going to do it on this video. Alright, so the G in guess stands for givens. What they gave us was a firework accelerates from a speed of 0 meters per second to a speed of 30. From 0 to 30, you can see a change in velocity. And this change in velocity, if you start at 0 and you go to 30, the change would be 30. So delta V is 30 meters per second. That's a given. The amount of time it took, so delta T, is 3.5 seconds. So these are both the givens in the problem. U stands for unknown. What is the acceleration of the firework? So I'm just going to put an A for acceleration and list that we don't know what that is. That's our unknown. E stands for equation. What equation are you going to use to find your unknown? Well, we have an equation for acceleration. The equation is delta V divided by delta T. The first S stands for substitute. We have givens. We know what these numbers are for these symbols. We're going to plug in these numbers into the symbols in our equation. So acceleration is equal to delta V, which is 30, divided by delta T, which is 3.5. And the last S just stands for solve. So acceleration will be equal to 30 divided by 3.5. So you'll have to do that in your calculator, and I'm not going to calculate that for you. 30 divided by 3.5 will give you your final answer, and that will be the acceleration of the firework. What I will talk about is make sure that you have a label. So whatever that answer is, make sure you label it. In this case, it would be meters per second squared. That's our unit for acceleration. Okay, example 2 and 3 somewhat go together. So one more time, I'm going to write out the guess method. Givens. Let's look at it. Do green this time. Rabbit is sitting still but then accelerates for 6 meters per second squared for 2.75 seconds. What velocity will he reach? Alright, so I see this number, 6 meters per second squared. It tells me that's my acceleration. So my acceleration is 6. He accelerates for 2.75 seconds. That's the amount of time. Okay. What velocity will he reach? I think that's all my givens. Those are the only two numbers I see. But if you look at it closely, there's a little bit more information. It says at the beginning, the rabbit is sitting still. If something is sitting still, you should know that means he has a velocity of 0, right? That's the velocity he starts with, so we call that the velocity initial. Velocity initial, 0 meters per second. It was kind of a hidden given in that problem. All right, unknown. What they ask you to look for is what velocity will he reach, meaning what will his final velocity be. E, equation. We do have an equation for final velocity. Vf equals Vi plus At. And luckily, Vi, A, and T, we know all three of those. So we're going to substitute them in to our equation. So velocity final will equal Vi, which is nice, is just 0, plus acceleration, which is 6, multiplied by the time, which is 2.75. Alright, the nice thing about this being 0 is this just goes away. We don't have to worry about adding 0 to something. So to solve this, the only step you have to do is multiply 6 times 2.75. Once again, do that calculation on your own and write your answer below. Since this is just a velocity, the label will be meters per second. It's not an acceleration. We don't have meters per second squared, only meters per second. Find that final answer. Okay, example 3. How far will this same rabbit travel during those 2.75 seconds? So I'm not going to write out the guess method for this because it's the same problem. We already have a lot of givens listed. And you should have calculated, we even know the velocity final now. But they want to know how far will that rabbit go. Well, we only have one equation for how far something moves. It's motion equation number 2. It's that long distance equation. Distance is equal to velocity initial multiplied by time plus 1/2 acceleration multiplied by time squared. This has to be the one because this is the only equation that has distance in it. So what we're going to do is substitute what we know into this equation. Alright, so once again, velocity initial is 0. It started from rest. So what we'll write below this is delta x equals velocity initial, which is 0, multiplied by time, which is 2.75. Okay, we're going to add 1/2 multiplied by our acceleration.
Desmond Lamb, if you're in the building, can you come to the main office? Desmond Lamb, if you're in the building, please come to the main office.
Our acceleration was 6 times the time, which was 2.75 again. You have to write it one more time. But don't forget, you have to square that. Squared. This is the equation you have to solve. Okay, so once again, there's something nice here. 0 multiplied by anything is just 0. So this whole left side of the equation just goes away, and you're only left with this half. Okay, I'm going to let you solve that, but I'll remind you, make sure you follow your order of operations. Before we can multiply the 1/2 and the 6, we have to use this exponent here. So the first step in solving this equation is to square 2.75. If you're using one of the standard calculators, there's not a square button, so just multiply 2.75 times itself. Then you can multiply it by the other two to see your final distance. Okay, so I'll leave that for you to solve. Make sure for distance, the symbol will be just meters. It's only a distance. Okay, for the remaining problems, I'm going to get you set up with what to do, and I'm going to let you do the rest. So a car has an acceleration of 10 meters per second squared. How long will it take the car to reach a speed of 75 meters per second? Alright, this one's a little bit different. I know acceleration. I know its final velocity. I'm assuming this car started from rest. So I also know the change in velocity. So the easiest equation to use for this one will be our original equation, delta V divided by delta T. Givens in this problem, I know what acceleration is. I know acceleration is 10 meters per second squared. I also know that the change in velocity will be 75 meters per second. I don't know what delta T will be. So for this problem, what you'll need to do is plug in what you know. So acceleration is 10. This will be equal to our change in velocity, which is 75, divided by delta t. We don't know what delta t is. So you need to do a little bit of algebra to get delta t by itself. It's kind of a two-step process. Okay, that'll be the amount of time it took. So make sure your label for this one will be in seconds. All right, that's all the help you get on example 4. Example 5. A truck slams on its brakes and slows down from a speed of 30 to a speed of 10 in 2 seconds. What is the acceleration of the truck while it is slowing down? Alright, so you have two options. You could use our original equation, the one we just used. Just make sure you understand what the change in velocity will be. Or you can use motion equation number 1. Motion equation number 1 was velocity final is equal to velocity initial plus acceleration multiplied by time. In this equation, we know a lot of things. They told us it started with a speed of 30 meters per second, so we know velocity initial. It changed to a speed of 10 meters per second, so we know velocity final. It also did this in an amount of time of 2 seconds. We know delta t. What is the acceleration of the truck? A, or acceleration, is the only thing we don't know in this equation. So what you need to do is plug in the values that you have for each variable and solve to find out what this acceleration is going to be. Since everything is in meters and seconds, your final answer for this problem, make sure you have a label of meters per second squared. Alright, and then our final problem, example 6, a skier going down a mountain can travel 100 meters in 11 seconds. If the skier starts from rest, what acceleration does she have? Alright, since they gave us a distance, we can remember that the only equation that has distance in it is motion equation number 2, the longer one. Okay, so let's think about things that we know. Things we know in the problem. 100 meters. We know the distance. It does this in 11 seconds, so we also know the time. If the skier starts from rest, so starting from rest, we know that that's the velocity initial. It's 0. What acceleration does she have? So the only thing that we don't know, once again, is the acceleration. So we're solving this problem to try to get A by itself. So let's think about this really quick. Velocity initial is 0. It says the skier starts from rest. So this left side of the equation goes away. We're only left with this. So let's go ahead and write this out. Distance is 100 meters. So delta x will be 100. This will be equal to, what's left over here is 1/2 our acceleration, which we don't know, multiplied by our time, which it says was 11 seconds. But we have to square that time. This is your equation to solve. We're trying to solve to get acceleration by itself. So remember, order of operations, square the 11 first, and then try to get the A by itself. Since this is an acceleration, again, your label will be meters per second squared. Alright guys, do your best on these problems. I hope this helped, and then once you are finished with this assignment, if you have time, move on to the next practice.